Welcome back. So, in the last lecture we were discussing about the consolidated drained triaxial test, and there we have seen that what are the different issues associated with consolidated drained test, and at the end we concluded that consolidated drained test is a time consuming matter, and therefore, it is not very popular in the community of geotechnical engineering, right. Therefore, the second type of triaxial test. So, basically in the last lecture we talked about three different types of triaxial test, if you recall. The first one was consolidated drained test, then consolidated undrained test and unconsolidated undrained test, that is CD, CU and UU, right. So, already we have covered CD test, and now today we will be talking about the consolidated undrained test. So, what are the different issues associated with this kind of test? Let's look at those things first, and then we will try to establish the mathematical equations. Now, in consolidated undrained test, basically the saturated soil specimen is first consolidated by an all round chamber fluid pressure sigma 3. So, it is very similar to your consolidated drain test. In that situation also you tried with the initial consolidation with the cell pressure, right. The same thing is done in case of consolidated undrained test. That is why the name is consolidated. That means, you are consolidating the sample, whatever soil sample you are putting inside the triaxial test apparatus. So, you are consolidating that sample with a chamber pressure or with a cell pressure of sigma 3, and then basically after the dissipation of pore pressure, because once you are applying sigma 3, right, all round cell pressure you are applying, and then you are allowing the soil sample to consolidate. So, therefore, the water will be draining out from the soil specimen under that pressure, that increment of pressure, that means sigma 3, and whatever excess pore water pressure will be getting generated, that will be getting dissipated from the soil specimen, and the soil will be ultimately consolidated, right. So, after the dissipation of pore pressure, so that means whatever pore pressure was built up for the application of sigma 3. So, after that dissipation of pore pressure, the deviator stress, that means the axial stress, now you are applying, that is delta sigma d. So, delta sigma d is increased to cause failure, keeping the drainage closed. Now, here actually you are getting the difference between your consolidated drained and consolidated undrained test. In case of the initial part is quite similar, that means both the cases you are consolidating the soil sample with the help of your cell pressure sigma 3. But when you are shearing, that means when you are trying to cause the failure or initiate the failure in the soil specimen with the help of the deviator stress, say delta sigma d, at that time you are keeping the valve closed in case of consolidated undrained test, which was not the case in case of consolidated drain test. At that time also you are keeping the valve open. That means, the drainage valve was open for the consolidated drain test throughout the test. However, in case of consolidated undrained test, the initial part, when you are allowing the consolidation with the application of sigma 3, at that time you allowed the drainage, at that time you kept the drainage valve open. But when you are actually shearing the specimen, shearing the soil to the failure, at that time you are not allowing the drainage. That means, you are closing the drainage valve and you are not allowing any type of consolidation. So, basically due to the application of delta sigma d, your pore pressure will be getting built up, right. So, that basically can be measured by some pore pressure measurement arrangement, that we will see later on. So, due to application of delta sigma d, pore pressure will increase, as I told you, because you are not allowing any drainage. So, whatever water specimen, fluid particle or the water particle or water substance is present in the soil specimen. So, that will be experiencing some increased stress in the axial direction, and due to that application of stress, basically your pore pressure will be building up, right. So, now both delta sigma d and delta ud are measured. So, delta sigma d you can measure anyway by the measurement by the loading ram application, right. So, you are putting some loading ram, and through the loading ram you are applying delta sigma. So, you can measure delta sigma, how much delta sigma you are applying, and also delta ud, which is getting developed, that is nothing but the pore pressure which is getting built up, okay, inside the soil specimen due to the application of delta sigma d. That also you can measure by some pore pressure measurement arrangement, and So, both the things basically delta sigma d and delta ud you are continuously measuring, okay, with some devices. Now, once delta ud can be measured, so delta ud can be expressed as A bar, okay, is equal to delta ud by delta sigma d. Okay. So, that is the ratio between delta ud and delta sigma d. So, that is delta ud is nothing but the pore pressure enhancement or the increase of pore pressure inside the specimen due to the application of delta sigma d, and of course, delta sigma d you are gradually applying in the specimen, right, where A bar is known as scheme turns pore pressure parameter. So, another scheme turn pore pressure parameter you covered or you discussed when we were discussing about the CD test. At that time, this pore pressure parameter was basically associated with the initial part of the test that was happened during CD test discussion, right. So, you have seen at that time we introduced one pore pressure parameter, that is B, right. So, there are two different scheme turn pore pressure parameter. One is associated with the initial part, that is when you are applying the cell pressure, and another part, another scheme turn pore pressure parameter, that is A bar, is associated with the second part, that is when you are shearing the material actually. Okay. So, now basically in this figure you can see the variation of deviated stress versus axial strain. So, as you increase delta sigma d gradually, your axial strain also will increase. Axial strain means in the longitudinal direction, because you are applying the deviated stress from the top, right. So, basically in this direction your axial strain will be happening. So, as you gradually increase delta sigma d, that means as you are shearing the material or the specimen, your axial strain will also increase, and in case of loose sand and normally consolidated, as already we have discussed that loose sand and normally consolidated clay, both the soil will behave in a very similar fashion, whereas dense sand and over consolidated clay, they will be behaving in a very similar fashion, right. So, in case of loose sand and normally consolidated clay, basically you will be getting as you increase your deviated stress, gradually your axial strain will also increase, and ultimately you will be getting a point here which will be defining the failure, right. After that you will be getting almost constant deviated stress. That means the strain will go on increasing, but there will be no increase in stress, deviated stress, right. So, this kind of say variation you will be getting between deviated stress and axial strain for loose sand and normally consolidated clay, whereas in case of dense sand and over consolidated clay you will be getting initial increase, it will reach some peak and then it will fall down, and finally it will be becoming, or eventually it will be becoming constant, right. So, this point will be denoting the failure, right. So, in case of dense sand and over consolidated clay, you will get the initial increase reaching the peak, and then further with further increase of axial strain, you will be getting the fall in the deviated stress. Okay. Now, similarly, because now actually in case of CD test, basically this you can measure, right, delta sigma d versus axial strain, but in case of consolidated undrained test, you can also measure how the pore pressure is getting built up, right, how the pore pressure is getting enhanced in the soil specimen. So, in case of loose sand and normally consolidated clay, as you go on increasing the axial strain, so as your axial strain increases, your pore pressure, that is delta ud, okay, it is also going on increasing, right. And once it is reaching the failure, and once it is become that curve, that is stress strain curve, whatever we have seen just now, delta sigma d versus axial strain. So, once it becomes constant, then your pore pressure will also become constant, because there will be no increase or no enhancement in the deviated stress. So, that will not cause any enhancement in the pore pressure. However, if you look at the dense sand and over consolidated, it is very important to note it. Now, it is really worth noting here. So, in case of dense sand and over consolidated clay, you will be getting initial increase in pore pressure and then further decrease in pore pressure, and it will be going to the negative side. So, negative pore pressure means something like your suction, right. So, the negative pore pressure basically with the axial strain, you will be getting some dilation in the soil specimen, and which will cause the suction in the pore pressure. So, that means instead of giving you a compression, it will give you some suction nature in the pore pressure distribution, right. So, that will give you the negative pore pressure. So, this is very very important and observation, an important thing to note. Okay. Now, in case of dense sand and over consolidated clay, the pore water pressure increases with strain to a certain limit. As I told you, it will increase to a certain limit, and beyond which it decreases, and becomes negative right. So, already we have discussed this thing. Now, why this kind of negative pore pressure you are getting? So, this decrease is because of a tendency of soil to dilate. So, in case of dense sand, okay, in case of dense sand or over consolidated clay, basically if you try to shear it, okay, so basically it will cause some volume expansion, right. So, it will cause some dilation in the soil specimen, and due to which you will be getting some suction. That means, when you are increasing the volume, so suppose you have this volume, and when you are increasing the volume due to shear, it will try to attract or try to accumulate the water inside. So, that means you will be getting some suction in the pore water pressure. Now, basically I mean this thing you can think of in this way, that why the dilation is really happening, right. So, it should come to your mind that in case of dense sand, why you are getting this kind of dilation, why not you are getting the dilation in the loose sand, right. So, now this thing can be explained in a very say easy fashion, right. Suppose you have this kind of say you have some short teeth. There are two halves, okay. So, this is your upper half and this is your lower half. So, in these two halves basically you are having the short teeth, and at the interface basically you are having the short teeth, and now you are trying to shear it, okay. That means, you are pushing the upper half with respect to the lower half. Now, what will happen? So, if you push it, because of this interlocking in the short teeth, you will not be able to push the upper half with respect to the lower half, right. It will be making some rigid arrangement, because of the short teeth will be having some interlocking effect, right. Now, once you want to shear it, now what you need to do? You need to lift it up little bit, right, and when it will be becoming like this, right, then only you can push it. Now, this lifting is basically known as dilation. That means, some volume expansion is happening. So, unless until you lift the upper half with respect to the lower half, you will not be able to shear it, right. Now, when you are allowing some expansion, when you are allowing some dilation, of course, you are attracting the water. That is how this dilation is happening, and this dilation will attract the water particles inside the soil matrix. So, and therefore, you will be getting some suction in the pore pressure, and that pore pressure will be becoming negative. I hope that you have understood the phenomena. So, this is a very crude way as well as the easy way to understand the dilation. Now, in case of consolidated undrained test, the major principal stress at failure. So, if I talk about total, okay. So, total the major principal stress at failure. So, that means the total stress is sigma 3 plus delta sigma d f, right. So, delta sigma d f is nothing but the failure deviatory stress at failure. So, sigma 3 will be always there, because when you are applying the cell pressure, at the time you are applying, that is all round cell pressure, right. It will be acting in the radial direction, it will be acting in the vertical direction, or in any direction if you consider, that will be the hydrostatic state of stress, hydrostatic pressure you are applying, that is sigma 3 plus the deviatory stress which you are applying until the failure which basically the soil specimen is experiencing, that is nothing but delta sigma d f. So, sigma 3 plus delta sigma d f is nothing but your major principal stress sigma t, sigma 1, right, which is acting in the axial direction, in the vertical direction, right. So, effective major principal stress will be therefore sigma 1 minus the pore water pressure which has been built up at the failure. So, that is nothing but delta u d f. So, sigma 1 minus delta u d f, that is nothing but your sigma 1 prime, right. So, in case of consolidated drain test, if you recall, your total stress and effective stress both are same, because in that situation that in this delta UDF was 0. I mean, if you recall our previous discussion that delta UDF was 0 for our consolidated drain test, because you allowed the drainage. So, there was no chance, no scope for this pore water pressure to build up, right. So, sigma 1 minus delta UDF is equal to delta sigma 1 prime in case of consolidated undrained test, whereas sigma 1 is equal to sigma 1 prime in case of consolidated drain test, right. Similarly, if you look at minor principal stress at failure, so minor principal stress, total minor principal stress is sigma 3, there is no doubt, because that will be acting in the radial direction or the lateral direction. So, that is, and of course, that is nothing but one of the principal stress. So, that is your minor principal stress, total minor principal stress. So, therefore, the effective minor principal stress will be sigma 3 minus delta UDF. So, delta UDF again, that is the pore water pressure developed or the built up at the failure. So, the sigma 3 minus delta UDF is equal to sigma 3 prime, right. If you try to compare this thing with your consolidated drain test, at that time the total minor principal stress was equal to effective minor principal stress, that is sigma 3 was equal to sigma 3 prime. Here in this situation it is not like that, rather you have sigma 3 minus delta UDF is equal to sigma 3 prime, where you are subtracting the pore water pressure which is getting built up during shearing. So, now if you try to plot this thing, that is whatever you have obtained from this consolidated undrained test, triaxial test, basically if you want to plot the shear stress versus normal stress, I mean graph, basically it will look like this. So, basically this I mean, so you will be changing basically these two solid mode circles, they are talking about the total stress at different confining pressure, at different cell pressure. So, for if you consider, for example, if you consider this small circle, basically at that time your confining stress was sigma 3, that is here, right, that means the total minor principal stress was here. Now, if you do the same test, okay, that is consolidated undrained test for the same specimen, but with increased say cell pressure, and say that is nothing but at this point. So, this sigma 3 again you are using the same sample, same test, okay, but you are just increasing the cell pressure. So, of course, when you are increasing the confinement, of course, you need to apply more deviatoric stress to get the failure. So, that is happening at this point. So, now basically these two I mean these two mode circles of course will touch the failure envelope, because in both the cases you are getting the failure. So, both the cases both mode circles must touch the failure envelope, and that is here. So, this is your Mohr Coulomb failure envelope, right. This is your Mohr Coulomb failure envelope which is touching the mode circle at these points, right. So, now this is nothing but your total stress variation. Okay. So, if you plot the shear stress versus normal stress graph with respect to the total stress phenomena, then basically they will be looking like this. But now, I mean from the earlier discussion, if you try to plot the effective stress parameters, then basically everything should be subtracted by an amount sigma delta UDF, right. So, this sigma 1, earlier case you are getting sigma 1 here, right, in a small circle. Now, this sigma 1 minus delta UDF is giving you sigma 1 prime. Similarly, this sigma 3 must be subtracted by delta UDF to get sigma 3 prime. So, you are getting this dotted mode circle which will be giving you the effective stress mode circle. Similarly, for the increased sigma 3, you can, this sigma 3 will come to this point, okay, with the subtraction of delta UDF. Similarly, this point sigma 1 should come to this point D sigma 1 prime, which will give you the effective measure principal stress, right. So, again if you draw the Mohr Coulomb failure envelope for the effective stress parameters, for the effective stress concepts, so that will be looking like this. So, basically what you are getting. So, this line, this dotted line is effective stress failure envelope, and it is given by tau f equal to sigma prime tan phi prime, whereas this is your total stress failure envelope, which is equal to tau f equal to sigma tan phi. But in both the cases you are getting the failure. One is your total stress concept. So, you are drawing the Mohr circle, you are drawing the failure envelope with respect to the total stress. In other situation, you are drawing the failure envelope with respect to the effective stress. Now, if you see these figures, in case of total stress, you are getting little bit flatter failure envelope, and that is defined by this angle phi, right. Phi is nothing but the angle of internal friction. Now, in case of effective stress, you are getting, this is your inclination of the failure envelope, that is phi prime. Of course, phi prime is greater than phi in this situation, right, whatever you can see. Now, if you basically, what I mean to say that if you express or if you report the angle of internal friction of a particular soil sample based on this consolidated undrained test, based on total stress concept, then basically whatever phi value you will be reporting, that will be always lesser than the actually developed effective stress phi prime parameter, right. So, therefore, I mean, if you design something based on this total stress parameter, of course, you will be underestimating the actual soil strength, which is nothing but phi prime, and which is eventually happening, right. I mean, phi prime basically. So, if you allow the drainage and if you allow sufficient times, the soil will be, I mean, ultimately the soil, the effective stress will be getting developed and effective stress parameters will be coming into the picture. So, if you design based on phi, that is the total stress concept, basically you are underestimating the soil strength, because ultimately you must get the effective stress that is nothing but phi prime, which is greater than phi, right. So, here actually you need to think about that, in which way you will be moving, either you will be designing with respect to total stress or you will be designing with respect to effective stress. Now, however, if you see this, see these plots, whatever plots we have seen just now, whatever may be the case, sigma 1 could be different from sigma prime, sigma 3 could be different from sigma 3 prime, but sigma 1 minus sigma 3, that is the difference between the major and minor principal stress, will be always equal to major and minor principal stress, difference between major and minor principal stress even in the effective stress situation. That means, sigma 1 minus sigma 3 must be equal to sigma 1 prime minus sigma 3 prime, right. So, that difference is not changing, only change is happening, that is sigma 1 is getting changed to sigma 1 prime from total to effective, and sigma 3 is getting changed to sigma 3 prime from total to effective. But however, the difference between sigma 1 and sigma 3 will be remaining same, the difference between sigma 1 prime and sigma 3 prime. So, the failure envelope that is tangent to all the effective stress Mohr circles can be represented by tau f equal to sigma prime tan phi prime, which is same as consolidated drain test, right. In case of consolidated drain test, you have got the same thing, that means you have got, because in that situation you expressed everything with respect to the effective stress parameters. That means, your failure envelope was I mean tau f equal to sigma prime tan phi prime, but the same thing you are getting, but in case of consolidated undrained test, you are getting both. You are getting the total stress failure envelope or the variation in total stress ambience, as well as you are getting the variation in effective stress ambience, right. So, both the things you are getting. When you are getting the effective stress parameters, at that time basically that is nothing but your consolidated drain test values, right. So, that is that it is, this statement is saying that thing only. So, CD tests on clay soil take considerable time, already we have discussed, already we have seen, that is in case of clay soil, you know that permeability is very low. So, the consolidation will take enormous time. So, if you perform CD test, that means consolidated drain test, that means you have to allow the drainage and you have to allow the complete consolidation. So, it will take considerable time, right. So, therefore, CD test is not very popular, not very common in practice. So, for this reason CU test can be conducted on such soils with pore pressure measurements to obtain the drained shear strength parameters. Okay. So, that is why what people do CU test with some pore pressure arrangement, pore pressure measurement arrangement, okay, and they measure the pore pressure, and once you measure the pore pressure, basically you will be getting both the representation, total stress representation as well as effective stress representation, whereas effective stress representation is nothing but the consolidated drain test result, right. So, that means if you perform consolidated, that means CU test, basically you will be getting the result, eventually you will be getting the result for CD test also. So, therefore, CU test generally people perform, and because drainage is not allowed in CU test, because you are not allowing the drainage, right. When you are shearing it, when you are applying the deviatory stress, you are not allowing the drainage, am I right. So, you are not allowing the drainage. So, therefore, in this test during the application of deviatory stress, so that means because drainage is not allowed in this test, in CU test, during the application of deviatory stress, the test can be performed rather quickly, agreed, because once you allow the drainage, you have to wait, right, as the water is expelling out or water is draining out, you have to wait till that period, till that time. In case of CD test, it was like that. So, you are allowing the drainage, but in case of CU test, you are not allowing the drainage, and therefore, you can perform the test quite fast, right, and therefore, CU test is very popular and very common, because the test itself is very quick, very fast. At the same time, whatever results, whatever plots or whatever representation you are getting from CD test, that also you can get from CU test. So, therefore, CU test is basically the global set, where CD is coming as a subset, right, something like that. So, anyway, I will stop here today. So, in the next lecture we will continue with CU test as well as UU test. Thank you very much.